a really good question, and one I hope we'll be able to answer for you.
As far as that all goes, it's been an age-old question. Which one is better? Should I zone with circulators? Should I zone with zone valves? And let me know, are you guys hearing any echoes right at this moment? If you want to type, I'm hearing an echo on my end.
I'm not sure if you guys are hearing an echo on your end.
So it's all right. Okay.
Okay.
You are hearing a huge echo.
Okay.
Let's see what we can do about that.
That's not good.
All right. Let's try this. Is that better? Nope, that's not better. Okay, why are we echoing? Let's try this. How about that? Whoa. Okay. How about that? Is that a big echo? Oh yeah. So are we better? Let's see. This is something new. This is something completely new. Let's see. Oh, I think I know what to do here. Yep, here we go. Give me one second.
Muted.
There. I think we got it. All righty. Now let's try it.
Okay, that's it. I had another microphone on. Very good. Okay, now let's get this show on the proverbial road. It is time to discuss the question of the day, the ultimate debate. Is it better to zone with zone valves, or is it better to zone with circulators? Every training class I do, it seems, this question comes up. We give out little index cards in some of our factory classes, and every class, there's at least 2 or 3 questions. Say, which is better, zone valves or circulators? Which should I do, zone valves or circulators? Well, both are really good questions, and there is an answer, and we're going to get to the answer. But first, we want to discuss the genesis of this entire debate. I don't think it's as violent today as it used to be. It used to be you had the zone valve syndicate and the circulator gang, and they hated each other. And both sides thought the other side was either an idiot or moron, and they would yell at each other, and it would sometimes get quite heated. So heated, in fact, that I do want to share with you a semi-true story. This happened back in, I think it was 1989, 1990 in Massachusetts, where I used to do business. We had a wholesaler just down the street from us who was they were our convenience store. I'd stop there a couple, 3 times a week on the way to work and pick up some stuff for that day's job or for the next couple of days' jobs. And I was on vacation, and I didn't go for a couple of weeks, and I finally went back. And as I'm pulling into the parking lot, I see a handful of vans parked on the far side of the parking lot with these guys out of their vans, kind of, shooting the breeze with one another and staring at the front door, and then they'd talk a little bit and they'd stare at the front door. Now, me being an idiot, I just drove right up to the front door and walked in because I didn't know any better. I walked into the front door, and there's another group of guys in there, and they're talking and doing the same thing as the guys outside are doing, and they're waiting for their stuff. And I didn't understand why all of a sudden there was a split. So I went up to the counter and I talked to the counter guy, Dennis, and I said, "Hey, Dennis, what's going on? Why are these guys outside and these guys inside? What's happening?" He says to me, "Oh, well, you haven't been here in a while, have you?" I said, "No, what's going on?" "Well, we had to split them up." I said, "Split who up?" "Well, the zone valve guys and the circulator guys." He goes, "What are you talking about?" He says, "The guys in here now, this is Wednesday, the guys in here now are the circulator guys. They get to go first. The zone valve guys have to wait until these guys leave, and then they come in." I'm thinking, what the heck are you talking about? He said, "Well, we had to split them up. About 3 weeks ago, we had a brawl in here between the zone valve guys and the circulator guys." And I'm sitting there dumbfounded going, what the heck are you talking about? Well, as it turns out, the leader of the circulator gang lost a rather large, lucrative boiler replacement job to a guy who was the leader of the zone valve syndicate. I mean, and it was like the Sharks and the Jets from West Side Story. They hated each other. And as it turned out, they were both in the supply house at the same time, both gangs. And the circulator guy started yelling at the zone valve guy for being a cheap, no good idiot so-and-so who stole this job by being cheap and not knowing what the heck he was doing, and he was ruining the market for guys like him who did it right. And he was just in this guy's face. And the zone valve guy said something bright like, "Oh yeah," and then it was on. And they had a knockdown, drag-out fight between the two of them, and their buddies joined in, and it was a rumble, just out of West Side Story. And what they wound up doing is they wound up splitting them up. All right. So the zone valve guys had to wait outside Monday, Wednesday, and Friday. They could go first on Tuesdays and Thursdays, and then the following week they'd switch. The circulator guys would go. The circulator guys would have to wait on Monday, Wednesday, Friday, and then on Tuesdays and Thursdays they could go first. It was idiotic, but that's exactly what happened. Now, what in the name of Ogie Oglethorpe is going on out there? Well, here's the deal. There has always been this kind of headbutting. My way's right, your way's wrong. No, my way's right, your way's wrong. That has mitigated itself, I think, since the early to mid-'90s in such a way that, and the reason it is mitigating itself has to do with radiant floor heating. The advent of radiant floor heating really softened the stances on both sides. How do you zone a radiant floor heating system? Well, you zone a radiant floor heating system with manifold actuators, right? What are manifold actuators on a manifold but zone valves, right? They're just simple zone valves, little electronic zone valves. And I think that showed the circulator gang that zone valves were not the spawn of Satan, okay? And I think as a result of this movement, the zone valve guys didn't think that the zone valve guys didn't think the circulator guys were any longer just mindless bullies. So they eventually learned to get a détente, I guess we could call it, if we were talking politically. The two sides were talking, and now the venom is not nearly as great as it used to be, although it is still there. Now, that doesn't answer the question which is better, right, or which is the right way to do it. So which is better? Who scores the perfect 10 in zoning? Does circulators score the perfect 10, or does zone valves score the perfect 10? And I think the answer is it depends on how you keep score. Okay, which is better, zone valves or circulators? It depends on how you keep score and depends on what you count. Does that make sense to you guys? We're going to get into the details of why that is, but I just want to do a quick check with you. How are we doing? Is it making sense? How's the pace, etc.? Let me know. Just give me a little something in here on your question form, just to let me know what's going on. All right. Just type in a little something. Okay, there we go. Sean, good man. Okie dokie. Very good. Thank you, Sean. Just so I know everybody's listening and hearing me. Okay, great. So which is better? It depends on how you keep score. If you're simply thinking in terms of delivering heat and comfort, all right, keeping people from freezing to death, keeping the rooms warm and comfortable, all right, keeping these things the way you want them, in reality, it's take your pick. It's the right path both ways, one way or the other. Take your pick. They're both good. They're both good. And thank you, Terry O, for the how about those Bruins? To you. But take your pick. Both work very, very well. And here's the other thing. I don't think anybody here would be able to tell the difference. We could all get together, get on a bus, and go to a bunch of job sites all throughout wherever we are. Some of the houses are zoned with circulators. Some of the houses are zoned with zone valves. If we didn't go down into the mechanical room, there's not a person on this webinar or on this internet, quite frankly, that could walk into a house without seeing the mechanical room, stand there for a few minutes and say, "Yeah, that feels like zone valve heat to me." It's just it can't be done. Okay, both work and both work well. Both are good, neither's better. There are differences. Now, the differences are something that you're going to have to take into account, and there's something that you're going to have to decide which is more important to you. Can you live with this? Can you live with this? Is this attractive enough? Is that someplace you want to go? So it really gets down to what decision do you wish to make for both you and your customers. Okay. So let's start off with why zone with circulators. What are the reasons for zoning with circulators? Well, obviously, why zone with circulators? Well, why not, right? Why not? It works, and it works very well. Circulators are, first and foremost, pretty doggone reliable, okay? Circulators are really, really reliable. The reason most folks give for zoning with circulators is that they are redundant. Hey, if I got a bunch of circulators and one of them fails, I got more circulators to deliver heat. If I got a zone valve job with one circulator, that circulator goes, we got nothing. I get that. Redundancy has value. It sort of flies in the face of the reliability argument a little bit, but the redundancy, I'm sure, can have value to certain customers. Maybe they're way, way out in the country, far away from anybody who can give immediate or fast service. Maybe there's a value to redundancy there. Maybe it's a job you're doing and it's way far away from your comfort zone. Maybe there's a value story to be told there in terms of redundancy. So we have reliability, we have redundancy, but I think this is the underpinning or the underlying secret, let's say, to why I think some folks prefer circulators over zone valves. It's kind of unsaid, it's below the surface, but believe me, friends, it is there. If every zone has its own circulator, it's freaking impossible. It's very difficult, if not impossible, to undersize a circulator. Right? It's very, very difficult to undersize a circulator. And we're going to illustrate that to you, gang, very, very vividly. So you'll see that, if I really think this through and if I really do the math, a 007 or a 3-speed circulator like a Takeo 0015 at lowest speed will be more than enough to deliver the BTUs I need if each zone has its own circulator. So let's take a look at that and kind of get into the nitty-gritty. Let's size a circulator. How do you size a circulator? Well, it's all based on the math. You got to know the heating load, and you got to know the heat load, and you got to know an approximate length of the run. You got to do a little bit of math. Now, a lot of guys say, well, I don't know what the heating load is. Well, if you're replacing a circulator, you're probably not going to do a heat loss for each zone. That's just not realistic. But understand, when you skip that step, everything else afterwards is kind of an inference/guess. Okay? Just make sure you understand that. If you don't do a heat loss, you really don't know what the load is on a zone. You can guess. You can measure the baseboard and multiply by 500. That doesn't tell you what the heat loss is. That simply tells you how much baseboard was installed, and that's a completely different thing. To really know, you got to know what the heating load is as best you can. Again, if it's a simple circulator replacement, I get it. You're not going to go through all this process. But if you're replacing an entire boiler and zoning with circulators, it may behoove you to do this, so you get an idea of A, what size boiler you should have, and B, get a better idea of what circulators to use. So you got to do that math. You got to know the BTU load for each individual zone. Once you have that BTU load for each individual zone, then you can determine the required gallons per minute flow rate using the universal hydronics formula, this math formula right here. This formula states that GPM is equal to BTUH divided by the product of delta T times 500. GPM is your gallons per minute flow rate. That's what the circulator has to deliver. Okay? BTUH is the heating load of the zone, typically under design conditions. You want it to work on the coldest day of the year. If you know it works then, it'll work the rest of the time too. So BTUH is your calculated heating load for that zone. And then delta T times 500. Delta T is your designed for temperature drop of the fluid as it goes through the zone. The designed for temperature drop. Now typically in residential hydronics we use a 20-degree temperature drop, meaning the water goes out at 180, comes back at 160, or if it's a condensing boiler, it goes out at 140, comes back at 120. It's what we design around, and that is applicable for fin tube baseboard. It's applicable for fan coil units, air handlers. It's applicable for cast iron radiation, baseboard, panel radiators, all that. It's a good all-purpose delta T. Residential radiant floor heating, you may look at a 10-degree delta T, simply to keep the floor temperature somewhat constant from front to back, inside to outside, especially if the tubing's going in between the floor joists. Tubing in a basement slab, you may very well see a 15 or perhaps a 20-degree delta T, because once the slab gets warm, it's warm, and that's that. So the delta T you choose is going to be very much application specific, but most North American residential hydronics we see designed around a 20-degree delta T. Now the 500 is a mathematical constant when we're using 100% water. It comes from multiplying the weight of 1 gallon of water, which is 8.33 pounds, times the number of minutes in an hour, traditionally it's 60, times the specific gravity of the fluid, water has a specific gravity of 1, times the specific heat characteristic of the fluid, water has a specific heat of 1, because after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour. That's all a lot of ones. 8.33 times 60 times 1 is 499.8. we'll call it 500. Okay? That's where that 500 comes from. And we're making some assumptions. That's the density of the water at room temperature, etc. But it's a lot of assumptions. This formula's been around forever, since way back in the early days of hydronics, when Gil Carlson first invented the Bell and Gossett system sizer wheel. All right, since that thing first came out, that's been the formula we've used. So it's a valid formula, and it's a very useful formula. Now that 500 is going to change, gang, just as a brief aside. That 500 is going to change the more glycol you add to a system. You start adding glycol into the system, that number gets lower and lower and lower, meaning the required BTU you need to, or the required flow rate you need to deliver the BTUs is going to go up, 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 okay? Because glycol doesn't transfer heat as well as water. And there's no standard guidelines for that. There's rough guesstimates. You have to look at the jug of each type of glycol you use and see what they recommend for a number. Typically, if you got a 30% glycol to 70% water mix, that's going to be about the number you're going to use is about 470 to 475. A 50-50 glycol to water mix, like for snowmelt or something like that, you might be looking at a number as low as 435. Okay, so that's going to affect things. But just to understand, if you're using 100% water, this formula as is a great way to get you going. It'll help you find the gallons per minute flow rate. GPM equals BTUH divided by the product of delta T times 500. Alrighty then, let's continue. We're going to do one. Let's see what we get. Let's say we have one zone of fin tube baseboard, and that one zone of fin tube baseboard carries as many BTUs as you can put onto a 3/4 inch pipe. That's 40,000 BTUs. That's the most you can get on a 3/4 inch pipe. That's as big of a zone as you could possibly have on a 3/4 inch loop. So we're talking big. This is a big honking zone, 40,000 BTUs. We're designing to a delta T of 20, and we are using 100% water. So let's fill in the blanks. Okay, this should be a very simple mathematical process. GPM equals 40,000 divided by 20 times 500, or 10,000. 40,000 divided by 10,000, we know our circulator is going to have to deliver 4 gallons per minute. Very good, Richard. You had it right off the bat, 4 gallons a minute. So our circulator is going to have to do that. That's half of the equation. That's half of the circulator sizing process. And we go through this exact same process too, gang, if we're sizing a circulator for zone valves as well, except we would use the entire flow rate of the entire job. Circulator, they don't have to do the entire flow rate for the entire job. When we zone by circulator, the circulator has to deliver the flow rate for that one particular zone. All right, let's continue. We have to, the second half of this is we have to calculate or estimate as best we can the head loss through that zone, There's two ways of doing it. There's the easy way, which estimates head on the high side. If you do it this way, gang, you will always be safe. It will always give you the highest possible head loss you could have for that zone, always. May not be accurate, but it's always safe. It's belt, suspenders, and wearing 3 pairs of pants all at the same time. It's very safe and very conservative. So I'm going to show you this way, and I'm going to show you a more accurate way, which you may or may not be able to do depending upon how close you can get to both the flow and head, or the flow and the loop length. So let's take a look. To estimate head loss the easy way, the first thing you want to do is, as best you can, measure the run. How long of a run are we talking about? And when we're talking about the run, we're talking about the length of the piping circuit from the gazouta side of the circulator all the way through all of the baseboard or all the radiation, yada yada yada, back through the boiler and back to the gazinda side of the circulator. If it's like a cast iron boiler, loop like that. So it's the entire length of run. We need to measure that as best we can. If we can get out there with a tape measure and measure it real accurately, great. If it's a retrofit and you don't really know, you can't get in there and measure the length, well now, guys, it falls under the heading of you must do the very best you can. In this case, you use your experience as a pipe fitter, and you use your experience as an installer, and you tap into your understanding of construction, of typical residential construction. How are these houses built? And then you just look at the dimensions of the house and say, well, first off, if I installed this, if I were pipe, how would I get through here? All right, if I installed it, how would I run this circuit? And then you estimate that and say, okay, based on what I know, how long could this circuit possibly be? All right, it's 20 feet down that way, and then I go up to the second floor. That's going to be another 10, 12 feet. Then I've got boom, boom, boom. Okay, I'm going to estimate that to be a 40. It's an estimate. Okay, it's not dead on accurate. It is an estimate. You got to estimate that run as very best as you can. Once you have that run, you have to now account for valves and fittings and crap that's in the way. So now you multiply by 1.5. You measure the run and multiply that run by 1.5. Essentially, you're adding 50% to make up for fittings and things. And if there are a lot of fittings in there, that makes sense. A 3/4 inch copper elbow, for example, has the same amount of pressure drop as 2.5 feet of straight copper pipe. So you have to take that stuff into account. Adding 50% allows you to do that. Now, measure the run. That's the total length. Multiply by 1.5. That gives you the total developed or total equivalent length. You start with your measured length, multiply by 1.5. That gives you your total equivalent length. Next, you're going to multiply that total equivalent length times 0.04. 0.04. And that represents 4 feet of head for every 100 feet of straight, properly sized pipe. That's 4 feet of head for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. What this formula does is it estimates the head loss at the maximum flow rate for each size of pipe. Okay? So for 3/4 inch copper, we're estimating the head loss as if we were running 4 gallons a minute through that. Whether we need to or not, we're estimating at 4 gallons a minute. If it's 1 inch copper, this formula will estimate the head at 9 gallons a minute. 1.25 inch copper at 14 gallons a minute, 1.5 inch copper at 22 gallons a minute. Okay, all of those pipe size guidelines are based on a maximum fluid velocity of 4 feet per second. That's how this formula was extrapolated. So as long as the pipe is sized properly for the load, this formula will give you a high estimated head loss for your zone. Okay. If I'm trying to run 14 gallons a minute through 3/4 inch pipe, this formula doesn't work, throw it out the window. But if I'm within my guidelines, this formula will always give you a high, reasonably accurate estimate. Does that make sense? All right. Does that make sense to you? Give me a little bit of feedback here, gang. Just let me know that we're all on the same page and everybody's happy, happy, joy, joy. All right. Let's see. Give me a little bit of feedback. Just type something on in. That would be good. Very good. Makes sense. Very good. Thank you, Steve. Thank you, Selburn. Hey, Stanley, how are you? Thank you very much. Okay. Thanks, John. Excellent, excellent. So far, so good. Terrific. So let's do an example the easy way. And then we're going to do the same example a little bit more accurately, and you're going to see the differences. Okay? So let's say our total run is 140 feet. First step will be to multiply that by 1.5 to allow for valves and fittings and stuff that's in the way. So 140 times 1.5, that's 210 linear feet. That's my total developed or total equivalent length. The total developed or total equivalent length. Okay? Now to figure out the estimated head loss for that zone, all right, we're going to multiply the total equivalent length times 0.04, and that gives us an estimated head loss for that zone at 8.5 feet ahead. All right, 8.5 feet ahead. So if we were to pair this up now, we need a circulator that's going to be able to deliver 4 gallons a minute at 8.5 feet of head. Peter White asked a question about pipe sizing and pipe diameter. So I'm going to just give you the quick guideline. So I don't have a slide on this, so just if you can jot this down. Pipe sizing is based on minimum for closed loop hydronic systems. Pipe sizing is based on minimum and maximum fluid velocities, a minimum of 2 feet per second, a maximum of 4 feet per second. To stay within those guidelines, we use the following pipe sizes for the following flow rates. If my flow rate is 2 to 4 gallons per minute, I would need 3/4 inch copper. If my flow rate was 4 to 9 gallons a minute, I'd be looking at 1 inch copper. 9 to 14, 1.25 inches. 14 to 22 would be 1.5 inches. 14 to 22 gallons a minute, 1.5 inches. 9 to 14 gallons a minute, 1.25 inches. 4 to 9 gallons per minute, 1 inch. 2 to 4 gallons per minute would be 3/4 inch. And again, that's based on those minimum and maximum velocities. Okay, I can run 22 gallons a minute through 3/4 inch pipe, but in a closed loop hydronic system, I don't want to do that. I'd have velocity noise and I'd erode the pipe from the inside out. So that's why those pipe sizing guidelines are there. Alrighty. .04 for just copper. Copper and also black iron pipe. Schedule 40 black iron pipe would work here as well. Schedule 40 black iron pipe, the only distinction we make is you want a maximum of 8 gallons per minute through Schedule 40 black iron versus 9 gallons a minute with copper. Everything else is still the same. PEX, you need to look at your PEX pressure loss charts that the manufacturers produce. That'll give you more specific guidelines for PEX because it's a little bit different. Okay. Does the pipe diameter affect the head? As far as a good question, Peter, as far as this formula goes, this formula is designed to estimate the head at the highest flow rate for each pipe size. Okay, so this formula actually applies to each size of pipe, provided my flow is within the guidelines for those sizes of pipe. Now, again, if I try to pump 14 gallons a minute through 3/4 inch pipe, this formula wouldn't work because the head loss would be through the charts because the pipe's too small. But if I'm within my pipe sizing guidelines, 2 to 4 for 3/4 inch, 4 to 9 1 inch, 9 to 14 inch and a quarter, 14 to 22 inch and a half, this formula fits all of these pipe sizes because it's based on 4 feet of head per 100 feet of properly sized pipe at the maximum flow rate for that size of pipe. Very good. And again, in PEX tubing, as we said, John, PEX tubing, you got to check the manufacturer's chart for pressure loss per foot, and that would be how you'd figure that part out. Very good. Let us continue. Now, 4 gallons a minute, 8.5 feet ahead. Well, that's where we would be. That's the requirement. 4 gallons a minute, about 8.5 feet ahead. Taking a look at this chart, gang, which circulator would you select? Okay. Just type in your answers there. Which circulator would you select based upon that operating point and those pump curves that are in front of you? All right. Let's see. Okay, we have Peter and Richard both selected 007. All right, Steve's 007, 007, 007, 007. This is a James Bond kind of crowd. All right. Yeah, in this example, the 007 would probably be your best choice. Could I choose that purple pump curve, number 4, which is the 006B? It's awfully close. Could I conceivably choose that one? Well, yeah, you could. You know what? And because I know we've estimated the head on the high side, we're safe. I think either the purple line for the 006B or the green line for the 005 would be perfectly fine and acceptable choices for this application. Both would work just fine. The thing is, you have to weigh cost and availability as well. The 006B, that B might be an indicator, that's an all-bronze circulator for domestic hot water recirculation. While the pump curve is very nice, I'm not so sure we'd use it because price-wise it's kind of out of the ballpark. It's all bronze, and we don't need all bronze. Just cast iron would be fine. Now, the 005 would also be a very good choice here. Again, but availability and price kind of play into the equation. The 005 is not a widely produced or widely available circulator. So in terms of both cost, availability, and in terms of performance, 007 would probably work very, very well there. Okay. Now Richard piped in on the 0015. Let's take a look at the 0015. And there is our operating parameter there. 4 gallons a minute, about 8.5 feet ahead. Clearly, what speed would you, if you were to use the 0015, which speed would you obviously have to put it on? It would obviously have to be on low speed. You'd be amazed, gang, that how often when you're zoning with a 3-speed circulator, you honest to goodness don't need the medium or the high speed. They don't come into play because they're just too much. We may see a scenario later on where you may need to do that, but in terms of zoning with circulators, low speed's fine. Now, with that said, let me ask you this. You guys go out on job sites all the time. How often do you see a 3-speed pump set at low speed? All right, you can certainly type in your answer. Because they're generally set at what speed? We call it contractor no callback mode, which is high speed. If low is good, medium is better, and if medium speed is better, well, high must be best. We get the most flow, we get the most BTUs, or at least if I put it on high, I know I'm going to have enough flow. And that's generally one of the things we see out there often is these 3-speed circulators set to high speed. When in most cases, when used as a zone pump, you really don't need to. You can leave it at low speed. Good question from John McDonough. Do you recommend an installer measuring the delta T of a system to set a multi-speed pump? That's a good question, John, and only that if it's the coldest day of the year, yeah, I think so. That would give you the best idea. But if it's 35 degrees outside, you're going to have tiny delta T's anyway, and because the pump's going to most likely be pumping more than you need. So yeah, you could put it at low speed, but that might be a situation where, all right, at 35 degrees I'm okay, but at 0 degrees or at 10 below I'm not going to be. So measuring the delta T is acceptable only when it's really, really cold out, either at or close to design conditions, I would think. If it's milder, there's really no way of knowing because we're not pulling as many BTUs out of the system, so the delta T is going to be smaller anyway with a fixed speed pump. So that's the yes with an asterisk. Yes, if it's really cold out, like close to design conditions. Otherwise, again, just doing the math is probably, just at that point, just getting the best possible idea of the length of the run, and then doing your estimate would probably help you. Knowing that if it's a 3/4 inch line, you're not going to have more than 40,000 BTUs on it anyway. It's just impossible. You can't. So if you can presume 4 gallons a minute at that point, get the best possible idea of the length of the run that you can, and then do the formula. That would probably be a better way, in my opinion. Okay. Good question. Let me know if that answers it for you. All right, now the right way, and again, this is not realistic in a retrofit application. No, it's not realistic. You're not going to be able to get in there and count all the fittings unless they give you free reign with a Sawzall, which is fun, but it's probably not going to happen. So how do we go about doing this? Well, again, in a retrofit, you can't. If you're doing the installation, maybe you can. But more importantly, I just want you to see what's going to happen here and how counting it out may be different from just adding one, multiplying by 1.5. So we use this chart, which gives you the equivalent length of straight pipe for different fittings of different sizes. So a 45-degree elbow is going to be equal to 1 foot of pipe, everything from 1/2 inch up to 1 1/4, 1.5 inches, it's worth 2.2 feet, and so on. A copper 90 is worth 2.5 feet of pipe. A full port ball valve, yeah, has pressure drop, gang. It's full port, I get it, but it still has pressure drop. And there's your equivalent length of pipe for different sizes. A globe valve, which is like a glorified stop and waste, is supposed to give you pressure drop, and here's how. And then T's, they're worth 5 feet of pipe. Okay, there's a lot of pressure drop in a T because you get 2 waters banging together, 2 ends banging together. And Venturi T's, of course, are supposed to give you pressure drop as well. So what you do here is you count, all right? So let's say we have 12 90s in this run at 2.5 feet each. Maybe that's low. It doesn't really matter. We're just doing this as an example. A couple ball valves at 2.2 feet each, and let's say we have 4 45s at 1 foot each. We add that all together. That is approximately 40 feet worth of fittings, all right, in terms of equivalent length. We add that to the 140 feet of pipe we measured, so now we're looking at 180 feet. There's our total developed or total equivalent length of 180 compared to the 210 that we estimated. Reasonably close. Now, here's where we get down to the nitty-gritty. We can actually use this chart. This chart comes from the Copper Development Association's Copper Tubing Handbook, and it gives you the pressure loss in PSI per foot of pipe for different types of copper, types K, L, and M at different sizes. You find your flow rate over on the left-hand side. We have 4 gallons a minute, and we're using 3/4 inch type M copper up top, so we see 0.015, all right, 0.015. PSI per foot of pipe. Make sure you understand this is in PSI for 1 foot of pipe. Now we all know, if we have a plumbing license, we all know that a column of water 2.31 feet high would have a gauge pressure at the bottom of 1 PSI. All right. In our world, 1 PSI of pressure drop is equal to 2.31 feet of head pressure or head loss. Okay, so just that's where that number comes from. So if we look at this chart, we know that at 4 gallons a minute, our pressure loss through 3/4 inch M is 0.015 PSI per foot of pipe. So let's multiply that by the 180 foot length. All right, the 180 foot length times 0.015 PSI per foot of pipe will give us a total pressure loss in PSI through that loop of 2.7 PSI. To turn that into feet ahead, multiply by 2.31. and that gives us 6 1/4 feet ahead. Now notice we're getting closer and closer to reality here. We went from 8 1/2 feet ahead down to 6 1/4 feet ahead. All right, so now the circulator really only has to do 4 gallons a minute at 6 1/4 feet ahead. If we were to look at our pump curve chart, now look at where we are. Okay, now we're at, now that number 3 pump, just the standard 006 would be an acceptable pump to use, but again, that's the curve for the stainless steel version. All right, and again, cost is going to be maybe out of whack. So again, you'd probably be looking at the 007. Now here's something for you to think about, guys. Whatever point you come up with here, ideally when you're selecting a circulator, you'd like to select a circulator whose pump curve is above that point, but not too far above. Okay. Now the 006 is right there. This is one operating point. Okay, this 4 gallons a minute at 6 1/4 feet ahead. That's an operating point or operating requirement that we have calculated. No matter which fixed speed circulator you put on there, and also no matter which delta P circulator, variable speed circulator you put on there, you may never, ever, ever see that point in reality. The system may never, ever work at that point, okay? Because both of those types of circulators will work on a fixed pump curve. A fixed speed pump curve, a fixed speed circulator, of course, is going to work on the pump performance curve, as you see here. It will always work somewhere on that line because energy in equals energy out. It has to work on that line. A delta P pump variable speed circulator will also work on a fixed pump curve. It's a funny looking inverted V-shaped pump curve, okay, but it's a fixed curve. So no matter what happens, the system will always work on that line. Okay. So to figure out exactly where the system will in fact work, we have to plot out something called a system curve, and there's a fancy math formula for it. But what a system curve is the unique fingerprint for each piping circuit. Every piping circuit in the world has its own unique fingerprint in terms of both flow and head. Once you establish the required flow and the head loss that you will experience at that required flow, mathematically you can estimate or you can calculate what the head loss would be at different flow rates through that circuit. The only reason you'd want to do that would be to plot out a curve. It's a mathematical curve. Okay, different points on the plot, you lay them out, you connect the dots into a line, and where that system curve line intersects the pump curve line will be the actual operating point of the system. For example, if we were to kind of estimate, just follow my cursor here, I'm at 0, 0 right now. If we were to kind of estimate what that curve would look like, it would follow this line kind of sort of like so. It shoots up like a rocket ship. All right, it's not linear. It shoots up like a rocket ship once you start building up flow. So realistically, if we use the 006, we would intersect probably at a little bit more than 4 gallons per minute, right at this point. If we continued on up, we'd intersect probably the 006B and the 005 right about at this point right here. And the 007, we might be right around here, maybe about 4 1/2 gallons a minute, maybe 4 3/4. If we continue it on up and we use the 008, we might be up here at about 6 gallons a minute. Okay? Now think about that for a minute. If we use that 008 or let's say the 0015 or the Grundfos 1558 at the higher speeds, we might be sending 6 gallons a minute through that system when we only need 4. Forget for a moment that there may be velocity noise. Now we're delivering 40,000 BTUs at 6 gallons a minute instead of 4 gallons a minute. All right, that's 50% more flow. All right, that's 50% more flow than we need. Ideally, what would ultimately happen is, under design conditions, the farther away you get from that operating point, the smaller the delta T in the system is going to be under design conditions. So you might in fact see a delta T at maybe 14 degrees, 13, 14, 15 degrees under design conditions on the coldest day of the year with that at 6 gallons a minute. And actually you can figure it out mathematically. What that means is the boiler's going to short cycle. All right, the boiler's going to short cycle more because the water's going out at 180 and coming back maybe at 165 or 167 or something like that. So that's going to create greater and greater boiler short cycling, which ultimately leads to a system that is not as economic as it could be to operate. So again, the further away your pump curve is from your operating point, the more you're going to pay for that in terms of a smaller delta T and smaller and more short cycling. Okay, great. So at this head of 6 something using a 007, will the pumps try to move closer to 13 gallons a minute? Okay, I see what you're doing here, John. You're reading this way, right? You're out here. No, because the head isn't capped. Okay, the head is a function of flow. So it's 6 feet ahead is not the cap. It says no matter what happens, 6 feet ahead through this system. That's not the cap. The relationship between flow and head is more mathematical. So again, think about a system curve. The system curve is going to kind of follow my cursor here and intersect somewhere right up in here. Okay, so it's really going to move about 4.5 gallons. So very good. The head pressure is not a cap. All right, it says it's 6 feet ahead, and that's that. Okay, it's not like a well pump. It's a little bit different. In a closed loop system, the system curve shoots up like a rocket ship, and where that system curve intersects the pump curve is where the system's going to operate. Okay, so again, you can answer your own question. The head pressure doesn't stay the same and move across the chart. Absolutely right. Okay, so we're not going to. This isn't the 6 feet ahead isn't a cap, so we're not going to operate out here. We're really going to operate right up in here someplace. Okay, good questions. Excellent, excellent. Now, same thing on a 0015. There's our requirement. Okay. Oops, I'm sorry. There is our requirement. So again, low speed is fine here. Low speed is absolutely fine. It's all we need. It's all we need. Okay? And again, if we were to map this system curve out, we might be here right about 4.5 gallons a minute at low speed. We might be up at about 5 gallons a minute or more at medium speed, and then we might be up here at about 6 gallons a minute at max speed. Okay, so you see how that will affect the system. Okay, it's going to work. You're going to deliver BTUs. No one's going to ever call you up and say they're cold. And they're never going to call you up and say, hey, buddy, that delta T on my system, and anywhere close to 20, get your butt down here and fix it. You'll never get that phone call. But you're going to find what you probably have is maybe some velocity noise that they may call to complain about, and you're going to have a short cycling boiler all the time, even under design conditions, and that's going to reduce the overall economy of operation. All right, let's think for a minute. And there is a valuable prize to be won for anybody who knows who that guy is and what cartoon series he came from. All right, the easy way, when we figured out our heat law, our flow in our head, the easy way was 4 gallons a minute at 8.5 feet ahead. Okay, we did that 1.0, 1.5.04. The right way would give us 4 gallons a minute at 6.25 feet ahead. Okay, so we see the difference. Now, no, it's not a selfie, John. That's not a selfie. I don't have a hat, anything like that. The rest may be accurate, but I don't have that hat. Anyway, now what would happen if we had a zone of similar length? Okay, because right now all of the easy way, when we did it the easy way, head was not based on flow at all. It was based on length, exclusively on length. All right. If we had a zone of similar length, but there was only 20,000 BTUs worth of heat load on there, so it was only a 20,000 BTU load on a zone. It's a completely different zone from the one we did. There's 20,000 BTUs worth of baseboard on it, but it happens to be the same length. Okay, it happens to be the same length. If we calculated head based on just the length, we would have 2 gallons a minute, 20,000 BTUs, 2 gallons a minute at 8.5 feet ahead, and that would put us in one circulator. But the reality is something completely different. If we base head loss on the flow rate, we'd see what we needed. So let's take a look at this. Same chart, okay? At 2 gallons a minute, the pressure loss in PSI per foot of pipe is only 0.004 PSI per foot of pipe. Multiply that times 180, all right, which is the total developed length when we counted everything out. Because again, closer to reality. We get 0.72 PSI. Multiply that by 2.31. Looky-loo here, we're at less than 2 feet ahead. We'll call it 2. 2 gallons a minute, 1.7, 2 feet ahead. Same length. The pressure, the flow rate required is much, much lower. Now look what we're at with in terms of head loss. It's much, much lower. So now we're way down here. The number 1 pump, the 003B, all bronze pump, would be fine here. That would be more pump than you need. Okay, absolutely more pump than you need. Understand this, the lower the heating load on a zone, All right, and again, smaller homes, things like that. The lower the heating load on a zone, under design conditions, the lower the flow rate is required. All right, and as a result, the head loss through that zone is going to be much lower. So again, you want to pick a pump as close to that operating point as possible. Now again, in this example, the 007 is probably going to be the one that's most commonly used. Now we're kind of far away from our, in terms of a pump curve, we're kind of far away from our requirement. So again, under design conditions, the delta T is not going to be 20. It's probably going to be a good bit less, because we might be up around in here again. We might be at about 3.5 gallons a minute instead of the 2 gallons a minute. So we have quite a bit more flow than we need. The delta T will probably be, under design conditions, probably a good bit less than 15 under design conditions. And the warmer it gets outside, that delta T is going to get smaller and smaller and smaller because the pump's running on a fixed speed. So this is what happens when we zone with circulators and when we, don't take the math into consideration. Because again, if we had done this just the easy way, we'd be at 2 gallons a minute at 8 feet ahead, which would be right up here. Okay, and that still would be the same pump. Okay, but you just see the difference. You see where we're at in terms of reality versus estimating. Yes, it is the Chili Penguin Show. It's not called the Chili Penguin Show, Stanley. It was Tennessee Tuxedo, and that was his walrus sidekick, Chumley, one of my favorite cartoons of all time. And again, in the multi-speed, 3-speed category, look where we are. Okay, so again, low speed, more than enough. I guess the point of all this, gang, is if you're zoning with circulators, low speed is more than you're going to need most of the time. Okay, so if you pipe things up with PEX, now PEX tubing pressure loss is going to be considerably higher because you might be using half-inch PEX or 5/8-inch PEX. Okay, smaller, more flexible PEX. So you may find that at 20-degree delta T, the pressure drop might be higher than you're looking at. Now then, in that case, the medium or the high speed may very well come into play, but you got to do the math based on the pressure loss charts provided by the PEX manufacturers. Okay, great. Now, why zone valves? Why zone valves? Well, zone valves, again, why not? Why wouldn't you zone with a zone valve? Zone valves are pretty doggone reliable. The wiring and the maintenance is a heck of a lot easier. Okay, it's a heck of a lot. It's 24-volt wiring, and you ever have to replace a head, you pop it off, pop the old one off, pop the new one on. Okay, and ball valve type zone valves are pretty reliable. They don't have the spring return part that can be the service issue. And space is important. We don't have the whole wing of the basement anymore to create our hydronics masterpiece like what this guy has here. Realistically, more and more these days, we're tasked with jamming 10 pounds of hydronic you-know-what into a 5-pound closet. So space is at a premium. Space is at a premium, and zone valves can certainly help us with that. And if you are concerned with wattage in terms of overall energy use, yes, 1 circulator and 5 zone valves will use less electricity than 5 circulators. Okay, how much? Well, don't oversell that, because it's in dollars and cents terms, it's not a lot. Unless you're paying 30 cents a kilowatt hour or 20 cents a kilowatt hour, and you may very well be. It's not a lot, because these are 80-watt circulators. They're like 80-watt light bulbs, and they don't run 24/7. They shouldn't really run continuously. I've never understood the concept or the attraction of continuous circulation. Put a relay on it, shut the darn thing off. The most efficient pump in the world is the one that's off. It doesn't use any energy then. So lower overall energy use, however, with this combination. For example, at 11 cents a kilowatt hour, which is the national average, 3 TACO 007s, a 3-zone system with 3 007s, 80 watts each, running somewhere between 2,300 and 2,500 hours annually. You're looking at a cost of electricity of about $66 a heating season for all 3 circulators. That's not per circulator, that's all 3 circulators. And you could extrapolate that out to about $22 a circulator. If, however, we went with 1 circulator and 3 zone sentry zone valves at 1.44 watts each, that cost is closer to $23 a heating season. So you can see we've cut that, and so you can see it, run the zone valves is about $1 a year. All right, we've cut that electrical cost by 2/3. That's what the marketing department will say reduces consumption by 2/3. A calculator is going to tell you that's $43 a year. Okay, over a 6-month heating season or 7-month heating season, that's about $6 a month. Okay? Just so you understand what we're really talking about here. Okay. Now, I get the whole redundancy argument. You know, if I zone with circulators and a pump fails, I got heat. If I zone with zone valves and a pump fails, I got bupkis. I got no heat. I understand that. Redundancy means you can never be too sure. However, there are two things. First, circulators are pretty doggone reliable, as we discussed earlier, and either way, it is a service call. Okay. A couple quick questions here before we get off circs. We are installing in-floor zones we are installing in flood zones requiring install on the first or second floors. Any change in pressure with different piping design? In terms of head pressure, no, it doesn't matter. Up and down doesn't really matter. In terms of head pressure. This isn't a well pump. It's a circulator. Okay, it's a closed loop system, and what goes up must come down, and what goes down must go up. Okay, so you don't have to. Your head calculations don't make a difference if the circulator's on the first floor and you're pumping down into the basement level. Doesn't make any difference. It's a loop, and the loop doesn't know up from down. It's all filled and pressurized. Okay. John McDonough asked, do you prefer delta T pumps or delta P pumps with zone valves? The answer is easy, delta T. That's what they were designed for. Delta P circulators, John, were designed for thermostatic radiator valve applications, modulating valves. With modulating valves, delta P pumps work fantastic. With on-off zone valves, delta P pumps, I wouldn't call them a true variable speed pump. I'd call them a how many speeds do you have open at any given point in time speed pump. You want a pump that's really going to vary its speed on a more fluid level. Delta T is the clear winner and clearly the way to go. And we can certainly discuss that at the end of the program. Now, sizing a circulator for zone valves. Okay, it's for the total flow rate of the job because that one circulator has to deliver heat to all of the zones. So it's the total GPM for the house. And then for head loss, however, we only have to calculate the worst case head loss zone, the worst case one, because it's a parallel piping system, okay? The reason is it's a parallel piping system. The water doesn't have to go, this circulator doesn't have to pump the water through this, pump a certain amount of water through this zone and then back through the other zone and then back through the other zone and then back. It only has to pump a certain amount of water through the worst case zone, all right, through the worst case zone. If I can overcome the head loss through that worst case zone, I can overcome the head loss through all the others with no effort at all, okay, because again, it's a circulator, it's not a pump. So we don't have to add the head of each of the zones together, just the worst case one, okay? So our total heating load for this job is 75,000 BTU. So that circulator has to give me the gallons per minute for the total job. And if we were designing to a 20-degree delta T, of course that would be 7.5 gallons per minute. So that circulator is going to have to do me 7.5 gallons per minute, all right? Now, we measure the worst case zone. We measure that longest run from the gazouta side all the way through that run of pipe, through the baseboard or through the radiators or through whatever it is out there, down through the return side, through the boiler, through the air scoop, and then back to the gazinda side. Now, in this example with a cast iron boiler, count the boiler, count the scoop as pipe. The pressure loss through an equivalent length of pipe is going to be greater than the pressure loss through the boiler or through the air separator, because there's both big open spaces in the piping, so you don't have to figure out what it is through the scoop. Just count it as pipe and you're good. Okay. So we measure that longest run, and let's calculate the head out here. Let's say we're same thing. Our biggest zone was 40,000 BTUs. The rest of the house was 35,000 for a total of 70,000. The long zone's 140 feet. Let's say we have 50 feet of valves and fittings. Okay. So the total length is 190. 190. Let's go to our PSI chart now. All right. We're at 0.015 PSI per foot of pipe. All right, multiply by 190, that's 2.85 PSI, multiplied by 2.31, we're looking at 6.5 feet ahead. All right, so now for the entire house, what pump would we need? Something that can do 7.5 gallons per minute at 6.5 feet ahead. I submit to you that it's the same pump, okay? In this case, if we had a 005, it would be dead on perfect, That would be absolutely perfect to run. With all three zones calling, okay, it would be perfect to run. It would be right on the line. Again, you'd probably pick a 007. And again, if we were to extrapolate out that system curve, we'd probably be here a little bit over 8, just a bit over 8 gallons a minute. Not perfect, but not bad. Not bad. If we had picked a higher head pump like this one up here, we'd be up at about almost 9 gallons a minute. Now we're starting to get into a bit more of an outlier. Okay, the delta T in the system under design conditions with all zones calling is going to get smaller and smaller and smaller. Does that make sense? All right, let's take a quick look. Okay, again, that's where it would run on the 007 line. Let's take a look at our multi-speed circulator, 7.5 gallons a minute, 6 1/4 feet ahead. Well, clearly we're going to have to go up a speed, right? Oh, no, I guess not. Now we're right on the line here for that thing to be operating. Now, not a bad choice with all zones calling, but we'd have to take a look at what would happen with just one zone calling when maybe we're back up here in the higher head area. We would be very concerned when we're operating in this area with just one zone calling that we could have banging zone valves. I'm sure everybody out here has had a job where the zone valves bang for one reason or another. Typically, zone valves bang when you use a steep curve pump, low flow, high head, steep curve pump, like the 0015, like the Grundfos 1558, and others. When you use a pump like that with zone valves, as zone valves close, the more zone valves close, the more likely you are to have banging zone valves because they're closing against higher and higher pressure differentials. They don't like that. Okay, they don't like that. That's why a steep curve pump is generally a poor choice for zone valve applications, most zone valve applications. Personally, the 3-speed pump, even though it's great that it has 3 speeds, would not be the right choice. Either this one or the Grundfos or any of the others would be a poor choice for zone valves because you'd have banging zone valves, and then you'd have to go install a pressure differential bypass valve and go to all that time and expense when you could have just put a flat curve pump in to begin with and be done with it, which to me, again, makes a heck of a lot more sense. Okay? Very good, very good. And again, if we set that to high to medium speed, we'd be at about 9 gallons a minute, and if we just didn't know, if we just said, they're all at high, I don't want to do anything, we'd be at almost 10 gallons a minute, which would be 1/3 more flow than we need. Again, under the worst case scenario, the coldest day of the year, the delta T on that thing's going to be itty bitty, and the boiler's going to short cycle. And if it was a condensing boiler, again, we'd have a similar problem. If the boiler was a condensing boiler, the water comes back warmer, it's not going to condense as much. It's just the way it is. Okay. Now let's throw the smallest zone in here as well. Let's say it's 1 gallon per minute, 10,000 BTUs. All right, that's 0.001 psi. Let's say it's only 110 feet long. All right, we're talking about 1/4 foot ahead. 1 gallon a minute at 1/4 foot ahead. That's down here. All right. Now, if we were to extrapolate out our lines, it would actually, with the 007, it would actually be up here at about 5.5 gallons per minute. Not great. Okay, not great. But we're not going. The zone valves aren't going to bang. We might have some issues with velocity noise, but the zone valves certainly aren't going to bang. Now, again, where we're going to be here, again, the 005 might be a slightly better choice, but that's kind of where we're at here. If we were to use our multi-speed circulator, again, we're out here. Okay, now, okay, I think you could make a case, and looking at where these numbers are, you could make a case, and I think it'd be a fairly decent one, that, now in this case, there really would be no difference between a 007 and a 1558, or I'm sorry, 007 and a 0015 if we ran the 0015 at low speed. In terms of performance, delta T, and that kind of, there really would be very little to no difference here. Okay, the danger comes in if, well, I want to make sure, I want to kick it in the pants and make sure we get the flow, I'm going to put it up to medium or even high, then we have some serious issues, okay, in terms of zone valve banging and then a dinky little delta T. All right, now if we were to put our delta T circulator, and this goes to your question, John, from earlier, if we were to put a delta T circulator on this bad boy, all right, delta T circulator, like this is the Bumblebee, it measures, it just monitors the supply temperature, the water coming out of the boiler, going to the system, and the return water temperature from on the common return of all of your zones. And let's say it's set up as, these things are at default set up for a 20-degree delta T. What it's going to do is it's going to watch those two temperatures and make sure, use those changing temperatures as information to tell it how fast to run, okay, to tell it how fast it needs to run. So in terms of always giving you the right flow, we calculate flow using the formula GPM equals BTUH divided by, GPM equals BTUH divided by the product of delta T times 500, delta T. There's no delta P in that formula, just delta T. So if we apply that formula and to come up with the best flow rate possible, we've got to understand if we monitor that delta T and speed the pump up and slow it down to try to maintain that 20-degree delta T, we're not imposing the delta T, we're just using the real-world information that the system's giving us to tell the pump what speed to run. And the real-world information is how many BTUs am I pulling out of the zone? Okay, the rooms are going to take the BTUs it needs, okay? And it's going to, the BTUs being removed will show itself in terms of return water temperature. All right. In a fixed speed pump, when a zone doesn't need as much room, all right, the delta T in the system is going to get smaller and smaller and smaller because the pump's still running the same speed. It's giving you the same flow rate. All right. In a delta T pump, as we pull more BTUs out of the system, the delta T is going to want to get wider. The pump's going to speed up to deliver the flow, and it's going to do vice versa when we need fewer BTUs. So what the Bumblebee is going to do is it's going to speed up and slow down first based on how many zones are open and closed at a given point in time and what combination. But also, it's going to speed up and slow down based on how cold it is outside. The colder it is outside, the more BTUs are going to be pulled out of the zone, the faster the pump's going to run, and vice versa. It's just the way it is. Okay? It is a truly adjustable pump curve circulator. It's a variable speed circulator, but really what varies is the pump curve itself. The pump curve moves to meet the needs of the system. A delta P pump has a fixed pump curve. All right, even auto adapt or no auto adapt, it's a fixed pump curve. Just like a fixed speed pump is a fixed pump curve. So let's take a look. The Bumblebee here, all zones calling, design conditions, 7.5 gallons per minute, about 6 1/4 feet ahead. Bam, there's your new pump curve. All right. The circulator is going to be running, it starts up, it goes right to max speed for about 30 seconds, establishes the delta T, and then it finds its happy spot. And that there's going to be the happy spot, 7.5 gallons a minute, 6 1/4 feet ahead. Bang. That's the speed we need to run to deliver the BTUs at that point for that system. Now, if only one zone was calling, that one little itty bitty zone, all right, you see we're at 1 gallon a minute, about a quarter of a foot ahead. Well, note that number 1 line. That's the minimum speed. Well, we're not going to get down to there. We just simply can't. Okay, we just can't. Realistically, the system's going to work right about there. All right, so we're not going to have a 20-degree delta T with one zone calling. We're going to put about 2.5 gallons or about 3 gallons a minute, a little more than 3 gallons a minute instead of the 1. That's just the way it is. But it's a heck of a lot better than where we were. We were up at 6 or 7 gallons per minute with the other pumps. Here we're a heck of a lot closer. And also note it's running at its lowest possible speed. So on the coldest day of the year, the circulator is going to be bopping back and forth between its lowest possible speed and just below its highest possible speed. As it gets warmer out, all right, that maximum speed is going to come down, 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 down because we're yanking fewer and fewer BTUs out of the system. And that's the beauty of a delta T circulator in a zone valve application. Cool. Bigger job, last thing, bigger job. Let's say we have total flow of 12 gallons per minute. Each zone's 40,000 BTUs. Total length, total developed length of each one is 200 feet. They're all the same. All right, if we quick math this out, that's 200 feet times 0.015 PSI. That's 3 PSI per zone times 2.31. That's 6 or 7 feet of head per zone. So now our circulator has to do 12 gallons a minute at 7 feet ahead. That's a big job. 12 gallons a minute, 120,000 BTUs, all right? 12 gallons a minute, 7 feet ahead. Where are we at? Right on the 007. Use a 007 there. It's a happy, happy, joy, joy kind of day. Right on the line, okay? And that will work just fine. 007 for that application. Big job. 120,000 BTUs, 3 fairly long zones. It works. If we were to use a 0015, a 3-speed pump, or with one zone calling, we're right here, okay? And the actual operating point would be where the blue dot is, okay? So again, that's a fine choice. That's a very, very good choice. Flat curve pumps and zone valves really do work well together because big changes in flow result in very small changes in pressure differential. Zone valves won't bang. If we were to choose a 0015 or a 1558 or any of the common 3-speed pumps, well, now we're going to have to run it at high speed to take care of all zones calling under design conditions. We'd have to run out there 12 gallons a minute at 7 feet ahead. We'd have to be running at high speed. But with just one zone calling, 4 gallons a minute at 7 feet ahead, you can see where we would actually be operating. We'd be way up there at about 16 feet ahead and looking at about almost 5.5, 6 gallons a minute. So again, delta T is going to shrink, but I'm more worried about that 16 feet ahead. We're going to have banging zone valves, all right? So that's the drawback of a 3-speed pump with zone valve applications, all right? Unless you're running it at low speed, and even then you still might get banging zone valves depending upon how the job's laid out. There's no advantage to it. Best to look for a flat curve pump or a delta T pump, variable speed pump for that type of application. All right, Bumblebee, not part of the equation here. Just not going to happen. It's not big enough. Okay, we wouldn't be able to do that. We could use a 007 VDT or even a 0011 VDT, which is a variable speed delta T pump. It's not an ECM technology pump. It's a standard 00 series pump with a special control on it to vary its speed based on delta T. That would be an application. You could certainly use that. 007 VDT would probably be a really good choice here. 007 or 0011, either one. Okay, but a Bumblebee, not going to happen. Alrighty, cool beans, man. This was fun, huh? All right, we've got, it's question time now. What we're going to do is just going to stay online as long as you guys have questions, okay? As long as you guys have questions, I'll stay on and we'll just chat nonstop. Let's take a look at some of the outstanding questions real quick. From John McDonough, we just replaced an existing boiler from 1965 that had two 007 pumps on the return. We installed zone valves on the return with the 3-speed pump on the supply. Customer asked about what happens if the pump failed, so we installed a second supply pump. Valves off, provided 3-way switching for the pumps. Customer could valve over on a backup. Yeah, sure. Sure, that would certainly work. That would be just fine. Again, like I said, backup pumps, and we've looked at different things that, some way to install backup pumps or some way to make it easy. And if that's of value to people, maybe it's something we can certainly look at. Okay. And John, you looked at what's the lowest flow rate on a delta T pump. Did that chart answer your question, John? Just let me know if that answered your question by looking at the pump curve chart. Very good. I would think this pump would cause the boiler to short cycle. Which circulator are you talking about there, Stanley? Are you talking about the 007 or the Bumblebee? Let me know. Which one do you think? Which one are you talking about? And can I use a Bumblebee? Can I use Bumblebee zone pump, zoning by pump? Absolutely. If you're going to use it's a good question that you bring up, John. If you're going to use if you want to use a variable speed pump as a zone pump, it only makes sense to use a variable speed pump that will in that application in fact vary its speed. A delta P pump would never vary its speed as a zone pump because there's never a change in pressure differential. It'll find its happy spot and that's the speed it's going to go at. What would the point be? If you want to use a variable speed pump as a zone pump, Bumblebee's a great way to go. I just got a bunch of pictures actually emailed me today of several jobs that were installed in several Bumblebees that were installed in just that application as a zone pump to get the pumps to speed up and slow down as necessary. Okay. Stanley asks, is it recommended to always use a pump higher than your calculation or drop to a lower pump based on the sizing information? Good question. Typically, Stanley, I think if you're close, if you've estimated the head in that estimating formula that we looked at, if you've estimated the head and you are close, you could certainly use the pump if your requirement's just a tick above your line, you'd be fine. Again, if you estimated it, because in reality the head's going to be a little bit lower because we know we estimate estimate on the high side. So yes, you certainly could drop down a little bit. A lot, you might be pushing it. Again, if you can always tell, but you can always tell what you really can do if you do the math. Okay, so that is the thing. So if you're not sure, then you want to go one higher. But again, what happens in reality, what happens, Stanley, is that guys will, you look at that and say, a 006 would have been a better choice in one of these applications. It would have been the best choice. But in terms of both price and availability, it's out of the ballpark. And the 007 won't be bad. It's not perfect, but it won't be bad. So again, you got to think that one through. So there's no hard and fast rule there. But if you estimate and your operating point, your requirement is just a tick below or a tick above your line, I think you're fine going down. Most cases you would be fine. All righty, Steve Lipsy has an appointment. It's a holiday weekend, so yeah, go get him. How often do you see pressure differential bypass valves used, or do most change to a differential pump to lessen the need? Scott, that's a great question. Pressure differential bypass valves, to my mind, are simply a Band-Aid for picking the wrong pump. I want to be perfectly clear about that. They are a Band-Aid for a self-inflicted wound, and that self-inflicted wound is selecting the wrong circulator for the job. Most pressure differential bypass valves I see installed are with 3-speed circulators, either ours or Grundfos's, on zone valve applications. When you ask guys why they do that, they say they're doing it because if I don't do it, the zone valves will bang. It's a steep curve pump, man. It's a steep curve pump. So when fewer and fewer zones are calling, those zone valves are closing against higher and higher pressure differentials, they will bang. So you must put in a pressure differential bypass valve in that application. But if you had used a flat, if the guy had used a flat curve pump, like the 007, a circulator that was designed for zone valve applications, where 3-speed pumps were not designed for zone valve applications. You use a pump designed for a zone valve application, you don't have a problem. You don't need a pressure differential bypass valve. Okay? Pressure differential bypass valves, let me say it again, they are Band-Aids for self-inflicted wounds. You have to use it because somebody insisted on using the wrong pump for the job. We're going to call it what it is, and that's what it is. Okay? It's not something European that we do to make our systems better. It's a Band-Aid for a self-inflicted wound. Are you sorry you asked now, Scott? But that is the reality of it. Okay, that is the reality of pressure differential bypass valves. 9 times out of 10 in typical applications we installed on these shores, they are not necessary if we had simply chosen the correct circulator for the job. And that's the long and short of it. A delta T pump and a delta P pump would both, in terms of variable speed pump, would eliminate the need for one, but you really want to eliminate the need for one, use a flat curve pump with a zone valve job and you're done. Okay, that really eliminates the need. Okay, terrific. Stan was asking about the Bumblebee. The Bumblebee our experience has shown it does exactly the opposite. It reduces short cycling. What happens with the Bumblebee is kind of neat. Is actually we've seen, and I think Anthony Reichow, you're on here. If you can, just raise your hand if you're capable of joining in. Anthony had a Delta T pump in his house, and he saw dramatic fuel savings in Philly in a colder winter in his home after changing from a fixed speed pump to a Delta T pump. But more importantly, one of the biggest things he saw was a serious lack of short cycling. In fact, sometimes zones would satisfy without the boiler ever turning on because of the wide firing differential. So we were actually able to use the residual heat in the boiler without making the boiler fire to satisfy some loads, which is kind of cool. So it did exactly the opposite. It certainly backed off the short cycling. So Anthony, you are here? Do you have your pump? Okay. Anthony, I've unmuted you. Do you want to share, just share with this group your experience with your Delta T pump? Because I know you know that story so well.
It's saved me. Can you hear me, John?
I can hear you pretty good. A little louder if you can hold your mic closer to you.
All right, John. Can you hear me now?
Little louder, me.
All righty. Hang on to your pantyhose. There you go. All right. Yep. Let me see. I'm going into my 4th year now with this pump, and I'm going to say my overall savings has got to be about 200 to 300 gallons a year. Now, that's a lot of money over 4 years. But when we first put it on, we noticed that we did about, we had about 2.5 tanks of oil the year prior, 15% colder the year I installed it, went down to a tank and 3/4, replaced the boiler the following year with outdoor reset, and now I'm down to about 320 hours at 0.6 gallons an hour, which comes out to about 230 gallons of oil. So, I mean, it just, what a pump, I'm telling you, I swear by him.
So the circulator helped get you a good part of the way, and then combine that with a newer upgraded boiler. Things miserly.
Oh yeah, I'll tell you what, recommend it. And the one thing that you said too, that we have guys starting to use them as zone pumps. And you know your load's going to change throughout the year, so is the speed of the pump. That'll prevent short cycling.
Very good, excellent. All righty, hey Anthony, thanks man. I'm gonna mute you again.
Hey, guy, man, see you.
Thanks for chiming in.
Welcome.
One of the very best trainers in the industry right there, Mr. Anthony Reichow, who just turned 60 this week. So everybody type in a little message to Anthony telling him happy birthday. He doesn't look 60. I tell you what, I've known him a long time. He doesn't look a day over 58. All right, you look good. And I hope you got that picture I sent you too. Anyway, a couple more questions. The Bumblebee question was about the 2 temperature points to measure, whether the boiler outlier is really to mix. The boiler outlet is really to mix all of the zones. Where you put your sensors, I guess if that's the question you're asking, John, your boilers, you want to sense the temperature at the boiler as the water leaves. That's the hottest water, or the water is going out to the zones. And then on the return side, you want to get your return sensor as close to the common return as you can, but not right at the boiler return, because that'll be falsified. So you want that at the right at the elbow of the common return, if you will, or maybe about a foot and a half downstream from that, away from the as far away from the boiler as possible at that point. So that's kind of where you would put those sensors. If that answers your question. Changing the pump is also a lot less expensive, says Scott. Absolutely, you're absolutely correct. You're absolutely correct. I brought up the Delta pumps before because we've had a job with a mix of inflow radiant, baseboard, and radiant panels with non-electric thermostat controls. Okay, so you'll have different pumps for the different jobs. A Delta T pump will actually work pretty well with thermostatic radiator valves. It'll work differently than a Delta P, but it'll work pretty well. The thing is, Delta P pump, the thing that makes a Delta P pump speed up and slow down is resistance against the impeller. More resistance against the impeller, that's a sign that the thermostatic radiator valves are closing. We don't need as much heat, so the pump slows down. Thermostatic radiator valves open, okay, less resistance against the impeller. That's a signal for the impeller to go faster, okay? But then the question always is, well, what happens when one TRV is closing and one TRV is opening? What does it do then? Well, it averages it out is what it does, so it's close enough, okay? That's why, again, it works on a fixed pump curve, so it's always going to give you more flow than you need, and it's going to let the TRVs kind of take care of themselves. A Delta T pump with TRVs is going to work the same way, only different, okay? The Delta T pump is going to work, like as a TRV closes, it means it's got enough heat, it's in that room, it's starting to close. In fact, the Delta T across that radius is going to get a little wider, right? Delta's going to get a little bit wider. That's, or should be, a signal to the Delta T pump to speed up, right? Which is kind of exactly the opposite of what it should be doing. But that's at that one moment in time, and that's for that one radiator. You get a bunch of radiators and a bunch of TRVs all doing different things at different time. It's going to do the same thing the Delta T pump or the Delta P pump does, and that's average it out. Okay, that's exactly what it's going to do. So that will be the process there. Okay, so what you can do is you can do, if you have zone valves, again, you can mix and match with Delta T, Delta P, or if you could all go Delta T. And again, Delta T is going to work very well with thermostatic radiator valves. Different than Delta P, but still work very well. Very good, very good. Okay, thank you, Scott. Thank you, Steve. Thank you, John. John Dirksen has a question. Is it a bad idea? Yeah, right, good. I can still talk. It's Friday. Is it a bad idea to use a Delta T pump in a primary circuit with a modulating boiler? If you're talking about the branch header, the distribution side, no, it's a very good idea. Certainly can be done. You don't want to use a Delta T pump on the boiler loop, okay? Yes, the boiler circulator. You want to use the circulator the manufacturer says you got to use. That's the pump you want to use. But on the distribution side, sure, done all the time. Absolutely a very good idea. Certainly can be done. John asked, I guess you're asking about Anthony. Was this a replacement oil boiler? Yes, it was. He had an older oil boiler, and then he replaced it with a newer one. So our guy out there, yep. All righty. Missed my answer when I broke up about a Delta T pump as the primary circulator, John. Yeah, again, not the boiler pump. You don't want to use it as the boiler pump. Use the pump that either comes with the boiler or the manufacturer specifies for a boiler pump. On the distribution side, on that side of the header, yeah, absolutely. You surely can use that. And really the best application is either with a hydraulic separator or better still a buffer tank. I mean, really buffer tanks to me with modulating boilers should be standard equipment anyway, regardless of what kind of pump you use. But sure, Delta T pump on that side of the hydraulic separator or oversized header or buffer tank, absolutely fun. Perfect way to go. Sure can do. Done all the time. All right, cool. Guys, I got to tell you, you guys had much better questions than yesterday's group. Smaller group, but great questions. Gotta love it. Gotta love it. And nobody said happy birthday to Anthony here. Guys, say happy birthday to Anthony. It's not every day a guy turns 60 years old. And you only turn 60 years old once, right? Sometimes not at all. And this is a big day for Anthony. So happy 60th, Anthony. Again, I just want to tell you. Happy birthday. All right, Tom Moore says happy birthday to Anthony. There you go. And you didn't tell me, did you get that picture? Just give me a private message or just type it in here. Did you get that picture yesterday? Because I made that just for you. All right. Yes, we are the smart guys. John McDonough turned 60 last year. And to get to 60, you gotta have socked away some experience and some wisdom and some knowledge. And the good guys like you guys, you share it. And that's a good thing. That's a good thing. All right. These questions keep on coming. If you have lazy math syndrome, your formula of length and 1.05 times 0.04 can be reduced to length times 0.06. Absolutely. I like to do steps. That's just the kind of guy I am. And the thing is, and you're absolutely right, Steve, but if you explain it 1.5 times 0.04, then you know what the 1.5 means and you know what the 0.04 means. You just say 0.06, you don't know what it means. But this way, it's a way of explaining what it all means. Very good, very good. All righty. All right, yep. Oh, boy, you got a lot of birthday wishes there, Anthony. Very good, very good. Excellent, excellent, excellent. All right, guys, keep those questions coming because this is all kinds of fun. Now, guys, just for your information, this webinar is being recorded and will be archived on Taco's The Neighborhood for you. And I'm going to make sure I got the audio this time. Like we did the same webinar in February, and I recorded it, but for some silly reason didn't get the audio, and I don't know why. So I hope I got it this time. I think I doubled up on my recording, so I think we're going to be okay. But we will, excuse me, archive that on the neighborhood a little bit later tonight. You will be getting an email probably tomorrow, if you haven't joined already, with a little link to join the neighborhood. And if you haven't joined the neighborhood, I seriously encourage you to do so. We have about 4 years worth of webinars archived there. And the neighborhood is also kind of it's a very unique forum for professionals only. It's separate from the FlowPro team. It's something very unique to Taco. It's an actual discussion forum for just professionals, and it requires a separate registration because it's owned by an outside agency. But you could start discussion forums or offer help to someone who's posted. We have videos, we have pictures. You can post job site pictures, start discussions. A lot of guys check in on it at least once, twice a day, and that's kind of fun. So you will get a link to join that, and absolutely encourage everybody to do so. And we have a grand old time. And most importantly, you will see the all of our webinars archived there. So terrific, guys. Well, hey, listen, questions seem to be drying up, so I just want to say thank you all, guys, and I do appreciate you being here. I hope everyone has a wonderful Memorial Day weekend, and if you if any of you guys left did serve our country, I'd like to offer my thanks and say thank you for your service, and it is an honor to be able to serve you back on this end. And remember those who gave their all for what we have here today, and that's the important part. And check my blog. Every Memorial Day, I post a Memorial Day blog. So if you want to check that out, there's a special one to my godfather, my Uncle Mike, who was one of 5 brothers who served in World War II and came back unscathed. So check that out if you would. I'd appreciate that. All right. Oh, a couple more questions. Very good. Very good. Let's see. Can you show a quick example of sizing a plate heat exchanger for domestic hot water for a home with 2 showers? Boy, Pete. No, I can't. Not for a flat plate. A quick example. I'd have to look some stuff up and be prepared to give that to you because I don't know off the top of my head. I think with flat plate heat exchangers, I think a flat plate heat exchanger is going to just be all about recovery. Because think of a flat plate heat exchanger as the same as you would think of an indirect hot water tank, but without the storage. Okay, with an indirect, you get storage of what's in the tank more or less, plus the rate of recovery from your heat exchanger. With a flat plate heat exchanger, you'd simply be dealing with recovery, the ability of what's the size of that heat exchanger and what can it do. So you have to have the specs of the heat exchanger, and then you have to know how many BTUs you have available with your boiler. As recovery is potential recovery is very much based upon how many BTUs you have in the boiler. All right. So a real easy way to figure recovery based on how many BTUs you have at the boiler is your net output of the boiler. Okay, not the input, but the net output, not the IBR output, the net, the DOE output, divided by 45,000. That will give you the potential recovery you would have in terms of gallons per minute. If you're talking about a 90-degree temperature rise of your water, so from 50 up to 140, okay? 45,000 comes from multiplying 8.33, weight of 1 gallon of water, times 60 minutes in an hour, times a 90-degree temperature rise, on your worst case. So that comes to 44,000 change. We'll call it 45,000. So your BTU output divided by 45,000 will give you the potential recovery that that boiler can produce. Then you match that up with the specs of the heat exchanger. Then you got to figure out what size pipe do I have to run to that heat exchanger. What's the head loss through the heat exchanger at the flow rate I need on the boiler side to do it, because it might be 10 gallons a minute, okay? And that's why you got to look at the specs of the heat exchanger and then see what you come up with, because sizing the boiler side pump is going to be critical for your heat exchanger. So I hope that helps. So I guess I could do a quick example right off the top of my head, more or less. Let me know if that helps, if that helps you. Okay, very good. What is PVR zone valve's working pressure? What is a PVR zone valve working pressure? PVR. What do you mean by PVR, Tom? There's different zone valves. I presume you're talking about max shutoff head. If that's what you're talking about, Tom? Again, it's different for different zone valves. The paddle type, the spring return types, like the Honeywells or the Eries or some of the others, they tend to have fairly low maximum shutoff heads, maybe 7 psi, and that's about 16 feet ahead. Easy. If you've ever blown past one, you know what I'm talking about, right? You look at a ball valve type like the Taco Zone Sentry. That's a ball valve, so it has the maximum working head of a ball valve, which is about 320 psi. So, or 125 psi, which is crazy amount of head. So you're not going to blow past the ball valve type. The paddle spring return type, you certainly can blow past that with an oversized pump. If that's your question. Very good, very good. Keep these cards and letters coming here, guys. Okay, this is good. You guys, again, your questions way better than yesterday's group. Way better.